So we missed your intro. If you want to try once more.
Oh, can you hear me now?
Yeah.
I'm a postdoc in the Cary lab also, and I'm just here to help out today. So I look forward to working with you all.
Thanks. So I'm going to get started, and I'd like to just first of all thanks everyone for who filled out the questionnaires before today's workshop. So we're working as part of this EDDI project, where we are developing teaching materials, standalone modules that will allow instructors to download all these materials and then teach them in their own classrooms. And collecting this data is a way of us to measure and quantify student growth from completion of these education modules. So the data that you are submitting will be synthesized later on into a paper to try and summarize the impacts that these are having. So I'd just like to thank you all for doing that. Now I will start my presentation. And then I will share my screen if I can find the buttons on Zoom. Okay. So can you see my screen?
Yeah.
Okay, thank you. So today's workshop is titled Understanding Uncertainty in Ecological Forecasts, and it's one of 8 modules as part of the Macrosystems EDDI project. You can access and find out more information about the modules that we have at our website, macrosystemseddi.org. And I'd like to thank the NSF for funding for supporting the development of this project. So just an overview of what we'll be doing today. I'll start off with this introductory lecture. This is going to be hopefully 25 minutes or so. And then the real aspect of this workshop is getting you to engage and work through a Shiny application that we have developed to explore and complete some activities that will help kind of develop your understanding of ecological forecast uncertainty. So the intro will introduce the concepts, where uncertainty comes from, how we can quantify uncertainty, and steps that can be taken to reduce forecast uncertainty. Then the activities, which are within the Shiny app, you'll first build different models for water temperature using real messy ecological data. Then you'll explore forecast uncertainty when you're generating your different forecasts. And then activity C will involve you working through a management scenario where you will be making decisions to try and manage forecast uncertainty. Also, if anybody has any questions throughout this presentation, please feel free to jump in at any time. I probably can't see the chat box, but I'm sure Mary and Whitney can keep an eye on that as well. So just to kind of set the scene, that globally ecosystems are changing, and this is in response to changes in the climate, but also changes in land use. And particularly freshwater ecosystems are experiencing change in terms of warming and thermal changes. And at the same time, lakes and reservoirs, as we all know, are key providers of ecological services, and understanding how they will change in the short term is critical to how we can help manage these resources. So before we start, would anybody like to offer up their thoughts on what a forecast is, or what they think a forecast is? Feel free to unmute and just shout something out. Oof. This is going to be a long workshop because I don't proceed until someone says something.
I can say something.
Yep.
I'm thinking a forecast is to tell like the future, to predict. It's what I am thinking.
Mm-hmm. Yeah, perfect. Thanks, Ben. Yeah, so a forecast is a prediction of a future event, and we define it as a future event with uncertainty, because we see that predicting what's going to happen, it needs to be associated with some degree of uncertainty or a probabilistic description of the potential outcomes. So it's particularly for events that haven't yet occurred, and it gives a probability likelihood of the event to occur, which is that measure of the uncertainty, which is what we'll be diving into today. And the idea is that a forecast is also actionable, that we can take this information that we have generated from this forecast and use this to take action to either in a management scenario or things like that to take preemptive action. So can you give people like to name some examples of things that we do forecast, or forecasts that you use in your daily lives?
The weather.
The weather.
Better.
What, sorry? Any other forecasts?
Climate.
Climate. Mm-hmm. Yeah. Any others?
Algae blooms.
Algae blooms. Perfect. Anyone else?
Sports.
Sports. Yeah. So we forecast many different things across many different aspects of different sectors of society. So things from weather and extreme weather events, such as floods, hurricanes, forest fires, to things like economic forecasts, disease transmission, election results, earthquakes, sports. Forecasts are integrated across all different aspects of society. So it's a really important skill set and knowledge to have about how these are generated and ways in which they are used. So what is the purpose of a forecast? We define these in kind of two distinct ways, which is one is for preparation. So for example, allowing us to prepare for a future event, with the example of being weather forecast and hurricanes. And for example, here is a schematic from the NOAA, which was for Hurricane Sandy, where they're showing a prediction of the potential path of the hurricane as it goes into the future. And then the second one is to take action to prevent something. So the example being like disease forecasting or fire forecast, what steps can be taken to prevent a certain outcome from occurring, such as the high transmission of a disease, or if there's a fire, if conditions are forecast that are ideal for fire, what steps can be taken by management to prevent or reduce the impacts of a potential forest fire. But we're focused today on ecological forecasting, and we define ecological forecasting as a prediction of future environmental conditions with uncertainty. And this is a schematic that we will use repeatedly to kind of demonstrate that the forecasting is a cycle, where it starts down the bottom left here of where you create your hypothesis through building a model, quantifying uncertainty, then generating the forecast, communicating the forecast to end users and potential stakeholders. Then as more data becomes available, we can assess our forecast. How well did our forecast do compared to observations? And then using this information, we can update our model, and then we repeat the cycle on a daily or whatever time scale which you are generating your forecasts. Oh, I just talked through, and yeah, you should prepare, remind yourself what slides are coming next. Yeah, so they're the steps that I just described. And today, in our activities, we're really focused in on these three steps here, which is quantifying uncertainty, which is the main aspect, but you will also be generating your forecast and communicating your forecast as well. So we have this quote, which I found really a really nice way of succinctly summarizing why uncertainty is important. It says that uncertainty is a fundamental characteristic of prediction, and no forecast is complete without a description of its uncertainty. And this is really kind of a way of saying how that if we talk about future events and we're trying to predict something, that we can't do it unless we give some sort of probabilistic likelihood or a description of uncertainty associated with it. And this is a report that was compiled about how we can do better at communicating uncertainty for weather and climate forecasts. So our focal question for today is, where does forecast uncertainty come from, and how can it be quantified and reduced? So uncertainty. So this is kind of giving you a scenario. What is uncertainty? We have 5 different thermometers in a room, and they're all reporting slightly different measurements. And this can be a result of different quality of thermometers, or using different methods for measuring temperature, or just the fact that all 5 of them exist in 5 different spaces in time. Even though they're in the same room, there might be slightly different measurements of air temperature. So which one is correct? Well, we can't really say with any, depending on the instrument, we can't say with any certainty that one of these is correct. So we can like to report that there is like uncertainty with this observation. And we can say, okay, these are all in and around 21.1 plus or minus 0.24 degrees Celsius. And this is just one way of describing uncertainty. And this is uncertainty related to observations, but it's to give it basically these kind of confidence intervals, or in which we have a high degree of certainty around that. But one way we can visualize uncertainty is using distributions. And this can be represented as a distribution of all possible values. So using the example below, when we have low uncertainty, we have high likelihood that it's around 21.1 degrees Celsius. But then if we have high uncertainty, if we have wider measurements, we can use a wider distribution to show that there is a likelihood that temperature could actually be down as low as 20 or up as far as 22. There's a wider range, and this is what you will be using throughout kind of the activity to kind of communicate this uncertainty in your forecasts. So 3 kind of key questions that I'll go through now in the presentation is, 1, where does ecological forecast uncertainty come from? How can we quantify the amount of uncertainty? And what are ways in which we can decrease uncertainty within an ecological forecast? So first of all, I'm going to just explain the difference between deterministic versus probabilistic forecast. So deterministic forecast is where we use a single line to represent the future. And this is not really a forecast, because it, like you said in our definition, it doesn't give include the uncertainty. So therefore we use probabilistic forecasts, where we give a range of future outcomes are represented, and each with a likelihood of each occurring. And we do this through kind of distribution, and this is represented by like confidence intervals, usually 75% or 95% confidence intervals. So similarly, again, that basically the forecast is a well-informed guess of the future. It will always have uncertainty. And this is just a plot showing forecast of air pressure, but just kind of getting how uncertainty affects kind of decision-making. So for example, with a 90% risk of a harmful algal bloom versus 10% risk of a harmful algal bloom in a lake affect our swimming plans. And this is how the communication of a forecast can potentially be used to influence people's decisions. And generally, uncertainty increases further out into the future, which makes sense in terms of that. We know how conditions are today, so then we have a better idea of tomorrow, while compared to 1 week from now, that there's going to be higher uncertainty associated with that. So today we'll be forecasting future water temperature for a lake site. And we're going to be using a very simple like linear regression model, where we're going to be predicting water temperature tomorrow, and using simple linear regression between air temperature, and we're going to be using forecasted air temperature as well to generate predictions of water temperature. And this kind of notation where m is the slope parameter, b is the intercept, and then t is time today, while t+1 is tomorrow. And this will be repeated in the activities. And then we'll also be using linear regression, where today's water temperature can be used to predict tomorrow's water temperature. So just diving into some of the sources of uncertainty. First one up is process uncertainty. So process uncertainty is related to uncertainty in the fact that our model doesn't capture everything that is occurring, and therefore it is an approximation of the real world. So therefore predictions from the model are going to be uncertain. When we have our model, like I showed in the last place, we have these parameters. So m and b are our parameters, and we're going to be approximating our parameters. So therefore there's uncertainty related to these 2 aspects. Then there's initial conditions uncertainty, driver data uncertainty, and we group process uncertainty and parameter uncertainty under the theme of model uncertainty. So I'm going to kind of dive into these in a bit more detail, but the further out into the future, they can propagate into the future, which means they increase further out into the future, which is what contributes to uncertainty increasing further into the future. So another kind of key term in terms of forecast is forecast horizon. So the forecast horizon is the length of time into the future for which forecasts are created. And as you can see in this diagram here, that t is time today, and then t+1 and t+2 is each time step into the future. And usually for like weather forecasts, these can be short term, so up to 7 days. But then if we're doing longer term forecasting, they can be on a years to decadal aspect. So when generating forecasts, we talk about ensemble forecasting. So I'm going to explain a bit about this. So instead of running just one single forecast, a model is run multiple times with slightly different conditions. So basically, we run the model maybe with different parameters or different driver data, and this allows us to approximate and generate a set of potential forecasts. And this multiple is called an ensemble, and each forecast run in an ensemble is called a member. And then we can use this distribution of forecasts. And each member of a forecast is equally likely. But then we can take that information from that distribution of members in the ensemble to characterize a probabilistic forecast, so that there is a 75% chance that it'll fall within here and a 95% chance that it'll fall within these ranges here. So now I'm going to step through the different types of uncertainty and kind of describe where they come from. So we start off with process uncertainty. So a model is an approximate representation of the real world. And what we can, process uncertainty is described as randomness that isn't captured in our model. So we can use a noise term to represent these real world processes that we know are not included in our model. So our simple model here is saying that tomorrow's water temperature is the same as today's. But we know this isn't true, and because this model is too simple, so we'll add this random noise component, because we know that we are not including what air temperature will be tomorrow, or we know that we're not including solar radiation that's coming in tomorrow. And this is known as process uncertainty. And just again, just showing how, stepping on to kind of parameter uncertainty. So a parameter in the model is a quantity that influences the model's output and is generally held constant. And parameters can be estimated using measured data, and we don't necessarily know what value the parameter should be. And to quantify this uncertainty, we can generate a distribution of possible parameter values. So our parameters in our model here are M and V. So therefore we can estimate our parameters and then use all those different parameters in those ranges, in that distribution, to generate potential future outcomes. Initial condition uncertainty refers to where we start the model, the starting values of the model. So if we want to forecast water temperature, the initial condition is the water temperature of today. And the reason why we have uncertainty related to initial conditions is because, first of all, we might, like in the example earlier, there might be uncertainties in the measurement of water temperature. Or two, it might be because we don't have a measurement from today. So therefore we use yesterday's measurement, but we attribute some uncertainty to that. So depending on if we have observations or not, we can have high or low uncertainty related to our initial conditions. Next one is driver uncertainty. So to make a forecast, generally a model needs forecasted driver data. So if we're using a model for water temperature that uses forecasted air temperature, then we also need to have air temperature into the future. And here is an example of an air temperature forecast, where this is an ensemble air temperature forecast, and then we can use this data and it propagates the uncertainty into the forecast variables. So then when we use this air temperature data to generate our forecast of water temperature. So where does ecological forecast uncertainty come from? It comes from process uncertainty, parameter uncertainty, initial conditions uncertainty, and driver uncertainty. So stepping into our second question is, how can we quantify the amount of uncertainty in a forecast? And this was using the ensembles that we generate, because this allows us to compare the contributions of different uncertainty sources and allows us to generate probabilistic forecasts. And then our third question is, what are ways in which we can manage uncertainty within an ecological forecast? So now I'm going to just kind of step through these examples here. So first step is we could improve our model. If we make a better model, then we can identify when the forecasts aren't performing well, and then we can identify ways in which they can be improved. So for example, if we just use the simple linear regression model, what we could do is potentially add in another term. We could add in forecasted air temperature, and this will help hopefully improve our model. Second step, we could collect more data. generally having more observations of our forecasted variable and more predictive variables can support the building of a more robust model and then allow us to estimate model parameters with more accuracy. We can use ensemble modeling. The more ensembles that we run, the better allows us for a better approximation. Because the idea being that if you run an infinite number of samples, you can approximate towards the future. But the more ensembles that we run using computers or high performance computers, it allows us to kind of quantify the uncertainty associated with this. And then the other step is, as new data becomes available, we can incorporate this, which allows us basically to kind of assimilate this data into our model. So then our model is overall improving and we can update parameters and things like that. So going back to our uncertainty. So if we have process uncertainty, the ways we can use to manage that is if we improve our model, use forecasted driver variables, or incorporate observation data. For parameter uncertainty, we can use more data to calibrate the model, or if the parameters in the model are potentially things that we could measure, we can potentially go into the field and measure them. And using the ensemble method of running multiple model realizations can help us improve or manage that uncertainty. For initial conditions, collecting more data, having data streaming directly into your computer, incorporating these observations and improving data collection methods. And then for driver and data, we can have, if we use better forecasts, better weather forecasts, and then again, using the ensemble modeling is a method to improve this as well, or to manage the uncertainty. So let's kind of set it up. And now today, what we are going to do is we're going to use a model to generate a forecast of water temperature in a lake using real data. So we will explore the sources of your forecast uncertainty, quantify its uncertainty, and learn how to manage the uncertainty of your forecast. So you'll be constructing 4 different models using different predictor variables. So first, you're going to be building a persistence model where it says that tomorrow's water temperature is the same as today's water temperature. Then you're going to be building a linear regression using today's water temperature to predict tomorrow's water temperature. Then you'll be using a linear regression using tomorrow's air temperature to predict tomorrow's water temperature. And then you will combine both of those models together to build a multiple linear regression, which will be using today's water temperature and tomorrow's air temperature. And then you will use these 4 models to generate forecasts, and you will compare how uncertainty propagates differently between different models. So we will be using water temperature at NEON sites, so the National Ecological Observatory Network. So you'll be using data that has come streaming in from all these different lake sites all across the contiguous US. And NEON itself is a continental scale observatory designed to collect long-term open access ecological data to better understand how US terrestrial and aquatic ecosystems are changing. So before we get started, just to outline some of the learning objectives of today's module. So by the end of this module, you'll hope to be able to define ecological forecast uncertainty. You will then explore the contributions of different sources of uncertainty to total forecast uncertainty, be able to outline how multiple sources of uncertainty are quantified, identify ways in which uncertainty can be reduced within an ecological forecast, be able to describe how forecasts arise and affects forecast uncertainty, and then explain the importance of specifying uncertainty in ecological forecasts for forecast users and decision support. So we'll just give you a quick overview of the different activities. So for activity A, we're going to split you up into breakout rooms of 4 students or 4 people in each breakout room. And you're going to be working together. You're going to be working as part of your group. You're going to select a site, build the water temperature models, explore parameters of the model, and then you're going to be building a better model. Then for activity B, you'll be exploring forecast uncertainty and comparing how they affect the different models that you've created. And you'll be exploring process uncertainty, parameter uncertainty, initial conditions, and driver uncertainty. And then for activity C, you will generate a forecast with total uncertainty, and you will quantify the different contributions of the different uncertainty and how that changes over forecast horizon, and then you'll be presented with a management scenario to decide where to release water from a dam using forecasts of water temperature. So, yes, so we will be using a Shiny app. So this is an interactive web page built using R. It has interactive plots and options embedded, so it allows you to kind of point and click. I'm going to do a quick demonstration.
I think that people have been invited to the rooms. I hope most of them are still here.
Oh, yeah. Okay, sorry, we shouldn't have them open. Oh.
Apologies for that. I didn't mean to open them.
Oh, okay.
They're closed. People will be coming back shortly.
Whoops. Jumped the gun. No worries. No problem. Yeah, so before we go into breakout rooms, we'll quickly just run through these options. But yeah, so we'll be using a Shiny app. So I sent out an email yesterday asking if people could download and run it locally. But if you didn't do that, that's okay. You can also, we'll be providing links so that you'll be able to open this in your web browser and then work through different activities there. So we're going to do this, but before we do that, I'm just going to do a quick demonstration of the Shiny app. So I'm just going to stop sharing the screen, and I'm going to pull it up on my computer. So, okay. 1 second, sorry. Just back to share my screen. So I'm just going to quickly show if people downloaded the GitHub repository, how to launch the Shiny app from the GitHub repository. So if you clone the repo, should have a file in there, either okay, I'm just waiting for the files to load. So in the module 6 folder, you should have a folder called app, and in there should be a file called server.org, and if you click on that, it opens, and then at the top of your screen, you should have a button that says Run App, and this will launch the Shiny app locally. If you didn't download the repository, that's fine. Like I said, you can access it online using either of the two different links that we have. And then you will get this, and this is our Shiny app, and it should be in your internet browser. And you can see that you can point and click and navigate your way through the different materials. There's questions embedded to kind of get you to, that I'll ask you to fill out as you work through. Sometimes the server crashes. So as you work your way through, I would encourage you just to kind of put these things in, but then if you want to save your answers, there's a button at the bottom of the screen, which is download user input. And this will download a .eddy file. So then if, for example, your thing crashes or you have to reload the page, because then if that crashes, you lose your data, what you can do is you can navigate, so you can see that, oh, they are there. But you go back to the introduction tab, and then there's a button here, which is resume your progress. And then here you can browse, and then it should bring you to your downloads folder, and you can upload that .eddy file, and then all your answers have been uploaded, and it will upload your models as well that you build, and then you will see that, yeah, it will fill out those. Okay, so I'm just going to stop sharing my screen if I can find Zoom control panel somewhere. Oh, stop sharing. But yeah, first of all, before we breakout. Does anybody have any questions or anything before we go into our breakout rooms? So we have, okay. So just before, I'm going to drop the links into the chat I'm going to split you up into 2 groups. So anyone whose first name is from A to L, you can use this link. And then we also have a different link which should work. So maybe, yeah, N to Z. So first name, you can use this link, and if you can launch them on your web browser. And then we're going to split you up into breakout rooms. Anything else, Mary, Whitney, or anything before we get started?
I don't think so. If you perchance end up in a room that only has 1 or 2 people, we will try and rearrange things so that you end up in a room with at least 3 to have company.
Yeah, the link might just take a while to load, so make sure you click on that. And yeah, we should be good to go. I'm going to stop recording now as well.